Welcome back to Probability and Statistics 1. This is Unit 3 on discrete probability. And in this set of slides, I'd like to introduce an example that will illustrate many of the concepts we've talked about up to now, including random variables, expected value, and probability mass functions. The example that I'm going to talk about is kind of a special one. It relates to things we've talked about already, including sampling with replacement, but it also relates to a very important probability model in its own right called the Bernoulli process. And so I'll leave that sort of undefined for right now, but as we go through and learn about this, we'll see more of how this actually is an example of what we call a Bernoulli process. So the example I'm going to talk about is called color sequences with replacement. And here's the definition. So an urn contains R plus G distinguishable balls, and little r is the number which are red, and little g is the number which are green. So every ball is painted either red or green, and there's R red balls and G green balls. And the balls are distinguishable. By that I simply mean that you want to think of the balls as, say, labeled too, like 1, 2, whatever, but just the first few of them are painted red and the last are painted green. So that's the situation, this urn with R red balls, G green balls. And what we're going to do is take a sequential random sample with replacement from the urn. So we'll take a ball from the urn picked at random, look at it, observe its color, and put it back, and then draw the next ball, observe its color, put it back, draw the next ball at random, and so on. So we'll call the kth draw a success if the ball drawn is red. Otherwise, we'll call the kth draw a failure. And often I'll use the term trial synonymously with draw. So if I say the kth draw was a success, all that means is that, or the kth trial was a success, all that means is on draw K, we had a red ball. And I'm going to kind of encode the results of this process in this sequence of indicator variables you see here. So I sub k is the indicator variable for trial number k. And it's simply 1 if trial k was a success, that is, if a red ball was drawn, and it's 0 if trial k was a failure. And the sequence, the ordered sequence of I sub k, so the sequence I1, I2, I3, is called a color sequence process with replacement. So think about what a sequence like that would look like. It'd be a sequence of zeros and ones, right? The zeros would indicate trials in which a green ball was drawn, and the 1 would indicate a trial where a red ball was drawn. So one of the first things to think about in terms of this process is what we call the success probability. Because the sampling is with replacement, right, the probability of drawing a red on any trial is simply the ratio of the number of red balls to the total number of balls. And this is, again, because we're sampling with replacement. So P, the success probability, is R over R plus G. And obviously 1 minus P would be the failure probability, and it's the probability of drawing a green ball. One of the features of this example, I guess you could say, is that essentially almost everything of meaning about this process can be expressed in terms of these success probabilities P and the failure probabilities 1 minus P. Some of the things we're interested in about this process would be basically properties of that random color sequence, the sequence of the I sub k's. So for instance, how many of the first, say, 15 draws are red? Or when would the first red ball be drawn? Did it occur on trial number 1 or trial number 5, or when? How many trials occur between consecutive red balls? Any sort of question that you can ask that deals with just the sequence of colors is a question that we would like to be able to answer. And so you can think of a whole host of those, I'm sure. So let's begin thinking about this process in terms of basic concepts like what's the sample space and so on. So the thing to remember is that the color sequence process is basically a process we've already studied, sampling sequentially and with replacement. It's just got this added twist that Some of the balls are red and the rest are green. But the sample space for the process is just the sample space for sampling sequentially with replacement. So it's a set of all vectors. If you look at, say, the process up to time n, up to the nth draw, the sample space would be the set of all vectors in Rn, such that each entry is a ball label, right? That'd be an integer between 1 and r plus g, the total number of balls. The cardinality of the sample space would just be r plus g to the nth power, right? Because you got r plus g choices for the first ball, and then we're sampling with replacement, so you have r plus g choices for the second ball, and so on. So the cardinality of the sample space is r plus g to the n. And again, the only added twist is that r of the balls are red and g are green. And just for specificity, you might want to think of the first R ball. Balls with labels 1 through R are painted red, and balls with labels R plus 1 through R plus G are painted green. We had defined these indicator variables. I sub k is just indicating whether draw k was a success or a failure, 1 being a success, 0 meaning a failure. These things are actually random variables. You'll recall the definition of a random variable is that it's a function defined on the sample space. Well, think about these indicator variables and an outcome of our process, right? An outcome of our process would be just a sequence of labels, the labels of the balls that were drawn. Here I'm showing you an example in a case where we have 3 balls, 1 red, 2 green, and consider the outcome in which in the first 4 trials, ball 3 was drawn, then ball 1, then ball 3, and then ball 2. So that's the outcome. And think about what these indicator variables would tell us about the outcome. I1 of that outcome, I1 of 3, 1, 3, 2 would be 0. Why? Because the I1 tells me the color of the first ball. The first ball was ball number 3, and that's green. So I1 would be 0. I2 tells me the color of the second ball. The second ball was ball number 1, that's red, so I2 of 3, 1, 3, 2 would be 1, and so on. So the indicator variables are actually functions defined on the sample space, and therefore we can think of them as random variables. I mean, from the point of view of just sort of thinking about the process as it plays out in real time, right? You would simply, to see what IK was, you would simply draw repeatedly from the urn, and on draw number K, IK, if you see that you drew a red ball, then IK would be 1. If you see that you drew a green ball, IK would be 0. And that gives you more of a sense of the randomness of the random variable. So in other words, indicator variables are random variables here. Let's think about the probabilities of various color sequences to get us started in this process. And for specificity, let's think of the case where, for instance, we have 11 balls in the urn, 4 of which are red, and 7 of which are green. What would be the probability of the color sequence 0, 1, 1, 0, 0 in this case, right? So that means what's the probability of first drawing a green ball, then 2 red balls in succession, and then 2 more green balls in succession? We want to know the probability of that. Well, the basic idea is to think about this as an event in our sample space, and then use the fact that sequential sampling with replacement, or actually with or without replacement, is a probability space in which all outcomes are equally likely. So the first thing we need to ask is how many outcomes do we have that have this color sequence? That is, green, red, red, green, green. And that's what I'm doing here in the second bullet point. The cardinality of that color sequence would be, well, you would just think about it from the point of view of counting, right? How many ways are there to choose the first ball so that it's green? Well, there's 7 green balls, so you have 7 different choices. For each of those, how many ways are there to choose the second ball so that it's red? So, well, there's 4 red balls, and so I could choose any one of those. So we have 7 times 4, and in the same way, there's 4 ways to choose the third red ball, 7 ways to choose the ball number 4, which is supposed to be green, and 7 ways to choose ball number 5, which is also supposed to be green. So you get 4 squared times 7 cubed is the total number of outcomes that have that color sequence 0, 1, 1, 0, 0. So the probability of that color sequence would just be the ratio of the number of outcomes with that color sequence, and again 4 squared times 7 cubed, divided by the total number of outcomes, right? And if you draw 5 balls, as we're doing here from the urn, there's what, 11 to the 5th ways of doing that, right? Because you have 11 choices for the first ball, 11 for the second, 11 for the third. Again, it's sampling with replacement. So you get 4 squared times 7 cubed over 11 to the 5th. And I want to write that in the way you see here. I want to split it up into 4 over 11 squared times 7 over 11 cubed. Because those are the, 4 over 11 is the success probability, and 7 over 11 is the failure probability. So we see this is really p squared, the success probability squared, times the failure probability cubed. And you'll always be able to do this, right? Because of the way sampling with replacement works. When you do a calculation like this, the sum of the exponents in the numerator is going to be the same as the exponent in the denominator. And so you'll be able to split it up like this and express that probability of a given color sequence in terms of the success and failure probabilities of the process in general. So as an exercise here, you might consider finding the probabilities of these color sequences you see here using the same kind of logic. And if you do that, you will, I think, see sort of the pattern, and you'll be able to have an idea of how you would compute the probability of any color sequence in the color sequence process with replacement. So we'll stop here for now. Think about those problems, and when we come back, we'll continue our exploration of the color sequence process with replacement.